This is the last section on colligative properties, part 1, part 2, part 3. This one has to do with osmotic pressure. Maybe you have seen this in your biology class. Let's say we have a U-tube, and on one side we have a pure solvent, and on the other side we have a solution. Separating those two is something called a semi-permeable membrane, which allows water, the solvent, to move back and forth. Well, these two solutions want to be at the same concentration, so we'll call that at equilibrium. And in order for that to happen, the solution with the side with the solution on it is going to rise up. Let's say we do not want to allow it to rise up, so we're going to apply a pressure, and that pressure is called pi. It's called the osmotic pressure. It's going to obey a law very similar to the ideal gas law. So what are you going to be expected to do? Well, they may ask you to find a molecular weight on an exam. It says here we have 0.070 grams of insulin. That would be our solute. And it's dissolved in 10.0 mLs of water, which would be our solvent. And it produced an osmotic pressure equal to 23 torr. And the temperature at which this was run was 25 degrees centigrade. So we've listed all our information. Well, remember we said, it's going to follow along with the ideal gas law. So when we're doing this type of problem, we would take the ideal gas law and put it into this form. Since I want to find the molecular weight, what I can do is do it in steps. And what I did is I kind of took it this way, all right? I said, well, what if I want to find my number of moles? That would be pi V divided by RT. What is my pi? Well, 23 torr, and I know that 1 atmosphere is 760 torr. The volume that they gave me was 10 mils, 0.010 liter, divided by R, 0.0821 liter atmosphere per mole Kelvin, and my temperature was 298 Kelvin, all right? So as I work through the problem, what I find is a very unusual number. 1.237 times 10 to the minus 5 moles. That sounds like maybe it's right or maybe it's wrong. Well, let's think about what is a molecular weight. Yeah, we could have gone down the path and just substituted it all in, but I think this way it makes you see it a little clearer. How many grams did I have? 0.070 grams. What are the number of moles I have? 1.237 times 10 to the minus 5 moles. That's how we did it back in 1210. What we come up with is 5659, or to be realistic, 5,600 grams per mole. Insulin is a polymer. I use this measurement a lot in industry when I was synthesizing new polymers. We make about 5 a day, and we give them to our analytical department in order for them to run an osmotic pressure measurement. They would come back to us with the pi value, and then we would plug in all the numbers that we had used to do the work to figure out the molecular weight. That is one way that you can use osmotic pressure. I included this problem because many of you are neuro, bio, medical. You're all headed in that direction. So here we have some blood, and it has a given osmotic pressure of 7.7 atmospheres sitting at 25 degrees centigrade. It wants to know what concentration of glucose, and really that is a molarity, and they want to know what concentration will be isotonic with blood. All right, so I'm going to use this equation. Pi is equal to MRT, and I'm going to rearrange it. I'm going to say molarity is pi divided by RT. And I have a pi of 7.7 atmospheres. I have the R, 0.0821 liter atmosphere per mole Kelvin, and I have a temperature of 298 Kelvin. And when I crunch those numbers through, 0.31 molar. Now this is sample exercise number 3. Do it is because you're going to the real world. It's nice for us to do these problems in Gen Chem, but let's say you're in medicine. Well, clinically speaking, they don't talk about molarity. If we have a 0.31 molar solution of glucose, that's going to be 5.3% of a mass percent or a weight percent. So again, I'm just trying to show you a little bit of a link between the two. In that problem, they talk about the physiological saline amount. So this is just a starting point. If you're planning to study anything, you're going to have to begin at the beginning, and that's kind of where this is. Reasons that I decided my thing jumped ahead. And basically, I wanted to also talk a little bit about real life. Many of you are taking bio at the same time. You have different backgrounds. But osmosis is something that occurs in red blood cells, and your IV must be isotonic with your intercellular fluids. So here we have a red blood cell, and essentially it is isotonic. We have in equilibrium, water going in, water going out. Here is something called crenation. And how does crenation occur? Well, if the bloodstream has a high solute concentration, there is going to be water coming out of your red blood cells, and that will happen in a hypertonic environment. If you have a low solute concentration, what is going to happen is water is going in, and you will have hemolysis in a hypotonic environment. I say this because I believe there is a mastering chemistry problem, and I just wanted to introduce the terminology and make this slightly a little bit more interesting. What else do we have? Well, one thing you'll probably see on your exam is something called the Van Hoff factor. It is symbolized by a lowercase I. Now, what's the truth about it? We have something called an ideal I, and that's where you do a count of the number of ions in a formula unit. Sodium chloride, 1 Na, 1 Cl, gives you a formula unit of 2. Again, you should know this. We're going to be using this further in this course. This is the equation. So I can insert this I value into my equation, and I can say if I'm going to calculate what is the actual change in temperatures for something like freezing, now I put the number 2 in there because there are 2 particles, and I come up with an actual delta TF of 0.372. Issue, I go in, actual is real, I measure it, and it is 0.348. So in reality, we have intermolecular forces. We have ions that attract themselves to one another. So I know chapter 11 was at the end of 1210. Everybody was tired. But again, you need the fundamental facts from that chapter to understand what's happening as we move forward. Here is the artist's rendition of the NaCl where they really haven't separated as they should ideally. 9. And, oh gosh. So how do we talk about this? Well, in your book there is this table, and the table talks about how many ions or molecules can be in solution. Notice that there are different molalities and how the molality is decreasing as I move from left to right. Notice how we're just going downhill. Well, when I have a non-electrolyte, the value is not going to change. You put 1 particle in, you have 1 particle out. But every time that you put in an ionic species or an electrolyte, or especially a strong electrolyte, you can see how the I value is going to change. I'll just pick on NaCl. Notice if I do the calculation at 0.1 molal, I have 1 value of I. If I do it at 10 times less concentrated, I have another value of I. If I do it at 10 times more less concentrated, I have yet another value. All of these values are going to approach the ideal value. So what we say is solutions behave ideally at very dilute concentrations. And again, this is the Van Hoff factor. It can be placed into any of our equations. It can be used to, this should be an F, it can be used to come up with different values. Please do your homework. I'll have some questions in the lecture Zoom that address this, but this tends to be a very normal midterm question.